Welcome to the Geometric Sequences podcast. All right, so we're going to do two problems in this podcast, and then we'll see some more in the next podcast. So first of all, we're going to find the common ratio here for our sequence. It's a little harder to look at the decimals. Let's change those to fractions, and I think it will make our common difference and our first term a little bit easier to work with. Okay. All right, so let's change that. So we have 1 here in the thousands place. So that's 1 over 1,000th. Okay. And then we have 1 in the hundredths place, so 1 over 100. And then 1/10. And then 1 and 10. All right, so let's find our common ratio. You could always take two successive terms, and divide one by the other. I think the easiest two terms to look at are these two, just in case you didn't figure out what the common ratio is. So our ratio would be 10 divided by 1, or 10. Right? So we just took the fourth term divided by the third term. I'll just write that in there. A4 divided by A3. Okay. Our first term in our sequence is 1,000th. So now we can write the rule, right, and then evaluate for n equals 12. Remember, when we write the rule, we don't substitute for n. It's only when we're evaluating for a specific term that we fill in the n. So here's our rule, okay, and it also could be called general term or nth term. Right, so we have an equals A1 was 1 over 1,000. And then times our common ratio was 10, and to the n minus 1 power. So there's our rule. To evaluate, we're just going to plug in 12 for our n. So we have A12 equals 1,000 times 10 to the 12 minus 1 power. All right, so that's going to be 1,000th times 10 to the 11th power. No need to use a calculator on this one. We just have to add 11 zeros to 10. So A12 is going to be 1,000th. Oh, and by the way, this one is in your notes. Times 10, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 extra zeros there. There we go. So this is hundreds, thousands. Oops, one of mine's in the wrong spot when I was counting there. Just kind of moved over a little bit. Let me just fix my comma there. 2, 3, and 1, 2, 3. So millions, billions, a trillion. So we have a trillion there, but not for long because we're going to multiply that by 1,000th. And all we have to do is cancel out 3 zeros. So now we have a billion instead of a trillion. Okay, and did I have enough there? 1, 2, 3. I think I do. Yep. So there we go. There's our answer. There's our 12th term in the sequence. Okay. All right. So rules aren't too difficult to write once you found your common ratio and your first term. And then plugging in, it's a matter of just raising to a power and then multiplying. All right, let's look at the next one. All right, so now we're not given the sequence. So here we were given the sequence, the beginning of the sequence, so we knew the first term. Right? Here we are not given the first few terms of the sequence. Instead, we're given two terms. We're given A3, which is 36, and we're given the fifth term, which is 324. So the first thing we have to do is find our common ratio. Right? So now when we set these up, we're going to have an be the later term. Right? So it's going to be the later term in the sequence, not the earlier term. It just won't work out. It won't work out very easily. Let's put it that way. All right, so later term in the sequence. Your A1, you're going to use your earlier term in the sequence. Oops. And the n minus 1, you're going to use the difference in the positions of those terms. So the difference in position, and this one's in your notes. Just add this to your notes as well. So difference in position between the later term and the earlier term. All right, so that's how we're going to solve for our R. All right, so we're going to use the terms we have and the difference between them, because this ratio will hold all throughout the sequence. All right, so we can use other terms so long as we represent their position correctly. All right, so our later term in the sequence is 324. It's the 5th term as opposed to the 3rd term. Equals the earlier term in the sequence is 36. We're looking for R, and it's 5 minus 3 is the difference in their position. All right, so now let's simplify. 324 equals 36R squared. All right, we're going to isolate our R squared, which means we have to divide both sides by 36. Okay, 324 divided by 36 is 9. And we know that when we solve for a square root, we have two solutions, a positive solution and a negative solution. So R here is either 3 or negative 3. Can't really tell from those two terms there, right? Could be either one. All right, so now we're going to consider both the positive and the negative values for R. I have this on this page, and we're going to solve for A1. I should tell you that. So we're going to solve for A1 by considering the positive and the negative values for R. In other words, we're going to substitute in everything else except for the A1. Now our AN could be any term in our sequence. It doesn't really matter. I'm going to use the first term because the n minus 1 is just going to be the difference between my terms. Okay? And it's easier if I use the smaller term. Right? I'll have a smaller exponent to deal with. So I'm going to do this on the next page because I'll have a little bit more space. Here we go. All right, so the things that we've found. And so our earlier term, remember, was A3 was 36. Right? And we know R is either 3 or negative 3. And we want to know A1. That's what we're looking for. Okay? All right, so we're going to solve it for 3, and then we're going to solve it for negative 3. So this one will be the positive, and this will be the negative case. Okay? And so AN is going to be 36. It's our any term. Okay. So an A1 is going to be our first term. That's what we're looking for. And then n minus 1 is going to be the difference between the third term. Or actually, I could just put, because the 1 we're keeping, right? Because that's the position of A1. The n is going to be the third term, right? Because we're working with the third term, right? Because A3 equals 36, n is going to be, and I shouldn't say third term, n is going to be 3, because we're working with the third term. There we go. All right, so for an, we're going to substitute any term we want. And why would you use the fifth term if you could use the third term, right? A1 is our first term that we're looking for. And n is 3 because 36 is the third term. All right, and now we'll just solve. All right, so an is 36 equals A1 times, oh, I should have written down, oh, I do have it written down, 3 to the 3 minus 1 power. All right, so that's 36 equals A1 times 3 squared. 3 squared is 9, so I have 36 equals 9. A1, and we'll divide both sides by 9 because we're solving for A1. So we have 4 equals A1. All right, so our rule could be AN equals 4 times 3 to the n minus 1 power. right? And then we'll evaluate for 8 in, actually no, let me evaluate for 8 right now, and then we'll solve for the other one. All right, so the 8th term, therefore, is going to be 4 times 3 to the 8 minus 1 power. Should have grabbed a calculator. So we have 4 times 3 to the 7th power. Let's see how long it takes me to walk over in the dark, because I don't have the lights on, so I can see the overhead better, to grab a calculator. Here we go. All right, and now I have to see it in the dark. So 3 to the 7th power, and of course I did not grab the best calculator in the world. There we go. All right, so that's going to be 2,187. And that's going to give us 8,748. All right, so that could be the 8th term. Okay. Let's solve for the negative case. So we have 36 equals, and a 1. This time, though, it's negative 3 to the 3 minus 1 power, which is 36 equals a1 times negative 3 squared, which is 9. And let me just put it in the front there. And so you can see that our either way, I'm going to divide by 9. I don't know why I put parentheses around a1. And my 9's looking a little A-ish. 4 is going to be our first term, no matter what. No matter what our R happens to be. So the rule, in this case, would be an equals 4 times negative 3 to the n minus 1 power. Maybe that's our rule. We can't tell here. And if that's the case, the 8th term is going to be 4 times negative 3 to the 8 minus 1 power, which would be 4 times negative 3 to the 7th power. And now it's going to be negative. So that's going to equal 4 times negative 2,187. And when we multiply that by 4, we're going to have negative 8,748. So it's possible we can actually have 2 different equations for the same sequence, just because of there's no way to know for sure whether it was 3 or negative 3, because both of them would have given us the same answer for the 3rd and 5th terms. All right, so that's the end of this podcast. And if you have questions, ask those in class. This was probably as tricky as these problems get, where we have 2 different possible rules. All right, so see you in the next podcast.